In this lecture, we will talk about radioactivity and then we will talk about alpha, beta and gamma decay. I am sure you will enjoy learning these concepts, especially the beta decay, because it is really interesting to know how does it happen. So let's start the lecture. So I have already told you that what is a radioactivity. Radioactivity is a phenomenon which happens when an unstable nucleus emits radiation. It is called natural radioactivity. Suppose this is a nucleus of certain atom and it is unstable, and then it emits an alpha particle. We know that this is alpha particle, and such radioactivity is called alpha decay if it emits alpha particle out of its nucleus, and as a result of that its mass number is reduced by 4 and it will lose 2 protons, because helium, we know, it is actually the nucleus of a helium, and helium has 2 protons and 2 neutrons, so it will lose 2 protons, so it will go back 2 steps in the periodic table. And of course now 2 particles are out of the nucleus, mean 2 protons and 2 neutrons, so of course its mass number will reduce by 4, and such a phenomenon is called natural radioactivity. And this is one example of radioactivity, because radioactivity can happen in different other ways. For example, alpha decay, beta decay and gamma decay. So we will study them in detail later. So this is how it happens. But one interesting question always arises, and you can ask me that one. That, okay, we know that an unstable nucleus radiates some radiation, and then this is called radioactivity, and then it becomes another element. Because we know when 2 protons are out of the nucleus, it will go back 2 steps in the periodic table. It will become some other element, it will not be the same element. But one fundamental question is there, that what makes a nucleus unstable? I mean, is there any condition that if it happens, nucleus will become unstable? Or what is a general concept of that condition that it is unstable? Or what makes it unstable? Before answering this question, let me show you the periodic table. So this is the periodic table and gives you some information. All the elements with atomic number greater than 83. So here you can see that atomic number is 83, means this element has 83 protons in the nucleus. So all the elements whose atomic number is greater than 83, mean from 84 onwards, these elements are called radioisotopes because they are radioactive material. They are radioactive materials, mean they will emit something and they will disintegrate. Disintegration means they will radiate some radiation, and as a result of that decay they will change into another element. So they are radioactive, all the elements with atomic number greater than 83. And similarly, all those elements with atomic number equal to 83 or less than 83, they are stable elements and they usually don't decay, or they don't have any radioactivity usually in normal conditions. But at least even these elements which are stable, mean those elements with atomic number 83 or less than 83, they have at least one isotope which is radioactive. And remember, by radioactive I mean they have radioactivity, they can decay. So mean all those elements whose atomic number is greater than 84, they are radioisotopes. They are radioactive, or they are readily available to decay. They will decay with any scheme they can. But even those elements which are stable, mean those elements with atomic number 83 or less than 83, all of these elements, they have at least one isotope which is radioactive, but not all of them, and even these elements are stable. So now let me answer the question that what makes a nucleus unstable. So I will give you the example of the simplest element in the periodic table, which is hydrogen. So you know that a hydrogen has one proton in the nucleus and one electron in its first orbit, and it is neutral, mean the number of protons and number of electrons are equal, and we know that they have equal but opposite charges. That's why it is neutral. There is no net charge in hydrogen atom. So this is hydrogen. Then I told you that what are isotopes. Hydrogen has two isotopes, deuterium and tritium. So what is an isotope? You know that they have same number of protons but with different number of neutrons. So if I add one neutron, you see it is still hydrogen, but it is not the base hydrogen, mean the most stable element in the periodic table, the simple hydrogen. It is not hydrogen because it has one extra neutron, but still it is stable. So it is isotope. The first was hydrogen, and this is an isotope of hydrogen because it has one extra neutron. So this is one isotope. Then it has the second isotope. If I add one more neutron, this is called tritium. The first one was deuterium. Deuterium was stable, but the second isotope of hydrogen, which is tritium, tritium is unstable. So if it is unstable, it means it will decay. In unstable nucleus will try to decay, I mean it will radiate some extra energy or some extra particles out of its nucleus so that it can go back to its relaxed condition, because everything wants to be at the minimum energy, at the relaxed state. So now it is unstable. So this isotope of hydrogen is radioactive. I told you that even the stable elements, they have at least one isotope which is unstable, and that will of course radiate something out of its nucleus, and that's why it is radioactive, I mean it will decay. But the fundamental question is what makes it unstable? So can you guess? When there is one proton and one neutron in the nucleus, forget about electrons. So if there is one neutron and one proton in the nucleus, it is stable. It is still isotope of hydrogen, but it is stable. If there is no neutron in the nucleus, it is hydrogen. It is the basic hydrogen, a stable atom of hydrogen, and it is stable. If I add one neutron, now there is one proton and one neutron. It is a stable, it is an isotope. If I add one more neutron, now it is unstable, and it is the second isotope of hydrogen, which is tritium. So can you guess what could be the reason of its? Because number, you see, proton is 1 and neutrons are 2. So if number of protons and neutrons, they are different, those nuclei are unstable, because the stable nucleus will have equal number of protons and equal number of neutrons. So that's why that when I told you that even the stable elements will have at least one isotope which is radioactive, because an isotope has different number of neutrons. So if some element has isotopes, of course a condition will come where the number of protons are different with number of neutrons, and at least we will have one isotope which is unstable in this case, because if I take out one, now number of protons and neutrons are equal, it is stable. Even if there is no neutron, it is stable. But if there is a neutron and then I add one more neutron, now proton is 1 but neutrons are 2. So this is what makes a nucleus unstable, and such nuclei will usually decay by emitting something out of their nucleus, and we will study what can they radiate out of their nucleus to go back to their relaxed condition. And let me tell you that this isotope of hydrogen, which is tritium will decay, and usually it has beta decay, and I will let you know at the end of this lecture that what is beta decay and how does it happen. So we have units for every quantity we measure. For example, if you want to measure speed, you have a unit, meter per second. If you want to measure mass, you have a unit for that, 1 kilograms. So similarly, if we have radioactivity, we should have a unit which can represent, or like we should know if we want to quantify what is radioactivity. One nucleus is more radioactive than the other. So how will we decide? So we should have a unit, right? So if we have a unit for radioactivity and it is 1, so 1 is equal to 1 disintegration per second. So let me show you what does it mean. For example, this nucleus of a hypothetical atom, and we assume that this is unstable and it decays and it has alpha decay. So, okay, so you know what is alpha decay. In an unstable nucleus will emit alpha particles out of its nucleus. So if the disintegration, for example, one disintegration in with first second, let's see, it emits one alpha particle out of its nucleus in 1 second. Then in the second it emits another alpha particle. Then in the third second it emits a third alpha particle, because it is emitting with every second, it is emitting one alpha particle out of its nucleus. Then it's in the fourth second it emits another alpha particle. Then similarly in the fifth second it emits another alpha particle. So this way it is going on, it is decaying. So when it emits one alpha particle, it is called one integration, one disintegration. And if it disintegrates in 1 second, mean one disintegration, mean it emits one alpha particle after 1 second, and then in the second it emits another alpha particle, then in the third second it emits another alpha particle out of its nucleus. And if this goes on, we will say its radioactivity is 1 becquerel. This radioactivity, I will say that the radioactivity of this element is 1 becquerel. So this is 1 becquerel. And let me remind you one thing, that for every disintegration, it will go back 2 steps in the periodic table. So it will become something else. Every time it will be a new element. Because for example, with the first integration, it will emit one alpha particle. So it will lose 2 protons. And then after second it will emit another alpha particle, so it will lose two more protons. So now it will become another element for each disintegration, and I am talking only about a single atom. So with every step it will move back in the periodic table. For example, if the material is suppose radium, and if it has alpha decay, so with the first integration it will become radon. You know that when it will emit one alpha particle, it will lose 2 protons, so 1 and 2, so it will become radon. This atom will become the atom of radon. And then with another integration it will become polonium with atomic number 84, because it will lose 2 more protons now after becoming radon, so it will become polonium. So with each disintegration it will go back in the periodic table 2 steps back in the periodic table, because every time it is losing 2 protons. So the radioactivity of such atom, I will call it 1 becquerel. So there are basically 3 types of decays, mean how a nucleus will decay if it is radioactive. We already know that if it is unstable, it will emit something and then it will go back to its relaxed position and it will become something else, because something has come out of its nucleus, especially when it emits protons out of its nucleus. If it doesn't emit protons out of its nucleus, then it will remain the same element, but it will just go back to its relaxed position or stable position. So of course it's easy, because if there are 3 basic decay types, that there are 3 ways a nucleus can decay, and those are alpha, beta and gamma decays. So first we should study what are those particles. Of course, it's easy. You can imagine that if it is alpha decay, nucleus will emit alpha particle. If it is beta decay, it will emit beta particle. If it is gamma decay, then a nucleus will emit gamma ray out of its nucleus. It's easy, but let's see what are those particles which will come out of the nucleus. So first one you are already familiar. This is alpha particle is helium nuclei. The alpha particles are helium nuclei, mean they are helium, they are only the nucleus of helium, because helium has 2 electrons in the first orbit around this nucleus with 2 protons and 2 neutrons. But the difference between helium and alpha particle is that it doesn't have any 2 electrons. So let me show you what is the difference between helium atom and helium nuclei, I mean the alpha particles. What is the difference between helium and alpha particles? So if I have 2 protons in the nucleus, this is helium nucleus. And then if I add 2 more neutrons, this is stable helium ion, because there are 2 protons but there is no equal negative charge to balance or to make it neutral. So this is alpha particle. So when there is alpha decay, this comes out of the nucleus. This is alpha particle, and if I add 2 more electrons to balance the charge in the first orbit, now this is helium atom. This is helium atom, and if there are no electrons in the orbit, this is alpha particle, and of course that's why it has positive charge of 2 protons. And if I add 2 electrons, now it will become helium. It is a neutral atom. This is the difference between helium and alpha particles. I mean, alpha particle is actually only the nucleus of helium. It doesn't have any electrons. So now let's see what is a beta particle. Beta particles are fast energetic electrons or positrons. So you already know what is an electron. So a beta particle is basically a fast moving and high energy electron or a positron. So you may not be familiar what is a positron. Positron is actually an electron. It has everything like electron, but its charge is positive. Its charge is equal to the charge of a simple electron, but it is positive. An electron has a negative charge, and everything else is same. So most of the students confuse positron with a proton because they think a proton has equal but opposite charge to an electron, right? Yes, it is true, because a proton has equal but opposite charge, mean positive charge, to that of electron. So it is the same case with positron. Positron has everything like electron, but its charge is opposite to the charge of electron, but it's equal in amount. So let me tell you the difference. A proton and electron. What is the difference between a proton and electron? We know that an electron has a negative charge, a proton has equal but opposite charge to that of electron. But this is not the only difference between the two particles. Difference is also between their masses. A proton is heavier than an electron, and in my previous lecture I told you how much, and I showed you the exact numbers. So a proton is different than an electron, of course, by the polarity of the charge they have. Electron has negative charge, proton has positive charge, and proton has a different mass than an electron. Similarly, if you have a positron, so now one thing is matching. Of course, their charges are same. I know that. Both have same charges and polarity of the charges is same. Both have positive charges. But one difference is still left. Electron, it is still electron. So it is everything of a positron is like an electron except the polarity of the charge. So now, okay, the charges are matching with a proton and electron, but masses are still different, right? Because this has mass of an electron, but a proton has its own mass. So their masses are still different. So a positron is not a proton. Remember that. Yes, their charges are same. Polarity of the charges is same. Both have positive charges and the charge is equal. But their masses are different. So they are two different particles. Don't think like a positron is like a proton. Masses are different. And now the last is gamma ray. What is a gamma ray? A gamma ray is electromagnetic radiation. It doesn't have any charge, it doesn't have any mass, it is just light. Light is a part of electromagnetic radiation, but it is just a small portion of electromagnetic radiation. We have many portions of electromagnetic radiation. So a gamma ray is just light. So it has no mass. You know, if you see the light has no mass and it has no charge. So that is the reason. So alpha particle has positive charge. A beta particle has either negative or it may have positive charge. So in most of our discussions, we will only take an electron, because a beta can be any one of them. So I will take only this negative electron to represent a beta particle in our next coming discussions. So we can say that alpha particle has a positive charge, a beta particle has a negative charge, and gamma ray has no charge. A alpha particle has a mass, of course, the mass of 2 protons and 2 neutrons. It is of course a heavier particle. A beta particle has only mass of an electron, so it is lighter than alpha particle, right? And gamma ray has no mass at all, so it is lightest of these three particles, and it has no charge as well. So next we will move to the properties of these particles. So how did we know that an alpha particle has positive charge, a beta particle has negative charge, and gamma ray has no charge? So that experiment is very simple. If I have positive charges on this plate and negative charges on this plate, so I know that there is an electric field set up between these two plates, because if I have a lot of positive charges on one side, negative charges in front of it, and then electric field is set up between these two plates. And the next is very easy, that if I do an experiment, suppose I don't know what is the charge on alpha particle. So if I have a setup like this, a positive plates, I have a positive plate and negative plate, and I know that an electric field is set up, and if I shoot this alpha particle, you know that this is alpha particle, and if I shoot it in between these two plates, what will happen? You know that alpha particle has a positive charge. If alpha particle has a positive charge, this positive charge on the right plate will push it towards the left. Of course, because two similar charges, they repel each other. So as soon as this enters between the plates, this positive plate will push this alpha particle towards the left, and at the same time the negative charge on the left plate will pull it towards each other, because they are oppositely charged. Alpha particle is positive and this is negative, so it will pull it towards the left side, and the positive charge will push it towards the left side. So what do you think will happen if it is fast enough and electric field is not very strong, and if I push this alpha particle between these plates, it will go, and as soon as it enters between the plates, it will start feeling the force, force from the positive charges towards the left and a pull towards the left by the negative charge here. So instead of going straight, it will go towards the left, 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 and it will go like this. You can imagine that, right? So if I trace the trajectory of alpha particle when it enters between the plates, it will be something like this, right? It will be deflected. It will not go straight. And if I don't know the charge on an alpha particle, I can do this experiment. And this is how we found that charge on an alpha particle is positive, because when it has a trajectory like this, and if I see this trajectory, I can see that when it enters the plate, it was getting a push from the positive charges towards the left, because it was positively charged, and it is also positive charge, and I know that two positive charge will always repel. Similarly, this negative charge is also pulling it towards this plate. So this is how it will get this trajectory, right? So we know that it has positive charge. So now it's easy to imagine what will happen if I push this beta particle. Remember that the only difference between an electron and beta particle is that beta particle is a fast moving electron with high energy. So if it enters between the plates, you can imagine what will happen. It will go and it will go like this because it is negatively charged. Now situation is opposite like to that of an alpha particle because now it is negatively charged. So it will get a push from the left side towards the right side and also get a pull towards the positive side because this is negatively charged. So it will go like this towards the right side. So if I trace the trajectory of a beta particle between two positively charged plates, it will be something like that, right? And this shows that a beta particle is negatively charged in this case. So now if I send a gamma ray between these two positive and negatively charged plates, what will happen? It will just go straight. So this is how we found that there is no charge on gamma rays. So if I make the trajectory of this, it will be just straight, no deflection. It will pass straight through the plates. There will be no deflection because it has no charge. This is how we found that a gamma ray has no charge. So this is not the only way we can find the charge on alpha, beta and gamma rays. There is another way as well. If we send the alpha, beta or gamma particle in a magnetic field, we can also find that what charge do they have. For example, we know that if I put a south pole in front of a north pole of a magnetic field will set up just like an electric field. And the magnetic field lines will start from north to south. So a magnetic field will be set up between these two poles. You know that a magnet has a north pole and south pole. So there is a magnetic field like that. And if I send these alpha particles between the magnetic field, I can find what charge do they have. But one important thing to remember, that if I send this alpha particle along the direction of the magnetic field, I cannot find anything. It will just pass straight through the magnetic field. I cannot see what charge do they have. Because if I want to use a magnetic field to find what charge a particle has, I have to send it in opposite, at an angle 90 degrees with the magnetic field. So I can either send it like this, it should pass like this, or I can send it from top inside, from the screen inside the screen. So here the situation is a bit difficult. So I will try to visualize it for you. So but just remember that whatever particle, and if I want to find the charge on that particle, it should not go along the direction of magnetic field like this. This is no way. I will not get any information. It should be at 90 degrees angle to get the information about the deflection, information about the charge on that particle. Because 90 degree, if I send it at 90 degrees, it will get maximum force from the magnetic field and maximum deflection, and that it will tell me. But if it is purely along the direction of magnetic field, I will not get anything. So just remember that one. I can send it at certain angle like this, and still I can get some information. But to get the maximum deflection, because in the case of electric field, we found the charge on the particle by the deflection in the electric field. So in the similar way, we will also get deflection in the magnetic field. And to get the maximum deflection, if there is any charge, so I should send it at 90 degrees angle. So to do that experiment, just imagine that you hold this magnet from the south pole, you hold it in your hand and you point the north pole towards the screen where you are watching this video. So just imagine you hold it from your hands from the south pole, and you point north pole towards the screen you are watching this video. And I hold this magnet from the north pole at the back of your screen where you are watching this video. Just imagine that I am holding this magnet from the North Pole and I am pointing it towards you from the back of your screen. So in this way, you are pointing North Pole towards my South Pole, right? You are pointing North Pole towards this screen you are watching the video, and I am pointing South Pole towards you from the back of your screen. So in this way, we are setting up a magnetic field, right? So in that way, we can represent the magnetic field like this. It is coming from you, from your eyes, into the computer screen and coming out of the back of your screen where you are watching this video. So these signs are showing that magnetic field. It is that magnetic field, right? In the way, it is same like you are holding a North Pole towards your screen where you are watching the video, and I have a South Pole at the back of your screen, and I am pointing right towards you. So the direction of magnetic field will be like this. It is coming from your eyes into the computer screen. So in this situation, if I send this alpha particle straight into this magnetic field, just see it. You are holding North Pole towards the screen. I am holding South Pole from back of the screen. And now here I inject this alpha particle into this magnetic field. You will see that it will also be deflected like this towards the left side. So if I want to draw the trajectory of this alpha particle, it will be like this. So it will be deflected towards the left. Similarly, if I send this beta particle, high energy, fast moving electron, it will be deflected towards the right side. So if I make a trajectory for this, it will go towards the right side. Of course, the amount of deflection will be different. It depends on the charges and the speed and of course strength of magnetic field. And similarly, if I send this photon, it will just go straight. So the trajectory for this gamma ray will be straight. So this is how we know that alpha particle is positively charged, because it is deflected towards the left side in this setup when the way we have set up the magnetic field. And because a beta particle was deflected towards the right, it has negative charge, and because gamma ray was undeflected, it has no charge. Now we also want to know two more properties of alpha, beta and gamma rays. The first is ionizing effect. What is ionizing effect? Ionizing effect is that if I place a material in front of an alpha particle which is coming out of the nucleus, then when after it enters into the material, of course, it is just a small particle, it will enter into the material, then how much it will interact with the atoms of that material. These circles are showing neutral stable atoms of that material. So when after it enters the material, how much it will interact with these atoms, because if it will interact, it may break some atoms. By breaking, I mean that it will strip off some electrons from their orbits, and as a result they will become positive and negative ions. You already know from the structure of an atom that it is neutral because number of protons and number of electrons are equal. But if alpha particle interacts with the atoms and it strips off some electrons from the atom, of course it will become positive ion, and then there will be negative electrons in the material. So in that sense, I am taking it will break some atoms, because the atom, a complete picture of the atom is broken now, because there are now no electrons, or some electrons are ripped off from the atom. So it is not in its stable or in its natural form. So this effect is called ionizing effect, and we want to categorize these three radiations or rays, that how much they have the ionizing effect if it enters into the material, how many atoms it will ionize, or if I place a material in front of a beta radiation, how much atoms it will ionize. And similarly, if I place a material in front of gamma ray, how much atom it will ionize. We will see in next section. So we will want to know like how much ionizing effect they have. Similarly, another property is penetrating ability. For example, an alpha particle is coming. I want to know that after it enters the material and how much it can penetrate, because after it is coming and then it will start interacting with the atoms and then it will just lose its energy and stop. So I will not see any alpha particle on the other side of the material here. So I will not find it here. So now if I send a beta particle, a fast moving energetic electron, it may enter and it can penetrate maybe deeper than alpha particle, but still I may not find it on this side. If I put a detector here to see if it comes out of the material, it may not come out of the material. Similarly, I want to know that what is the penetrating ability of a photon. It may just come and come out on the other side of the material and I can find it. So I will say that this has a greater penetrating ability, and beta particle has less penetrating ability than a gamma ray, and alpha, it has less penetrating ability than the other two, beta particle or gamma ray. So we will see what is their properties regarding these two quantities. So let's see ionizing effect of alpha particles. So here is an alpha particle. I put a material in front of alpha particle. Here it comes and it enters the material, and what happens? Okay, so it means when it enters the material, it will ionize large number of atoms of that material. So it means it interacts with the atoms of that material, and because of that interaction, of course, it will ionize those atoms. They will become positive and negative ions. You see, it will ionize a large number of atoms in that material, and of course I can understand that, because if it does that, it will lose its energy, so its penetrating power will be very less. Of course, when it loses all of its energy, how will it penetrate too deep into the material and come out of the other side? No, it will lose all of its energy because it has ionized a lot of atoms. You know, you need a lot of energy to ionize one atom, and if it ionizes a lot of atoms in that material, it will lose its energy and it will just stop there. So an alpha particle has a large or high ionizing effect or power, but very less penetrating ability, because it cannot penetrate deeper into the material, and you know the reason, because it will lose all of its energy in ionizing the atoms of that material, and of course it will stop there. Now let's see what will happen to the beta particle, a fast moving energetic electron. Let's see in the next slide. Okay, so it will also ionize some atoms of that material, but not that much. So it means it will still have some energy left to penetrate into the material. So a beta particle has less ionizing power but a greater penetrating depth, because it will have some extra energy to go deeper into the material than alpha particles, because it doesn't ionize a lot of atoms of that material. It will ionize some atoms but not as much as in the case of alpha particle. So it means it has higher penetrating ability but lower ionizing power. So as a result, it will go deeper but not that much. So what will happen if I place a material in front of a gamma ray? Gamma is just a light, so we always call it a ray, not particle. Okay, so when gamma ray enters a material, it does ionize some atoms, but a minute amount of atoms. So it will ionize a minute amount of atoms of that material, and as a result, it will have a large energy. So it will go deeper, and even it will come out of the other side of the material. So it has the greatest penetrating ability than the other two particles, but it has lowest ionizing power or lowest ionizing ability, because it will not ionize a lot of atoms of that material when it enters that material, and as a result it will be left with a lot of energy. So instead it will just pass through the material with that energy, and it may even come out of the other side of the material. So these are their properties. So what is an alpha decay? When an element, which is of course unstable, and it releases a helium nuclei or helium ion. So just remember that this is not a neutral helium atom. A neutral helium atom has two electrons in the first orbit. But when in the alpha decay, which comes out of the nucleus of this atom, this is just a representative image. Like here you can put any element you want which is involved in the alpha decay, and then this is the mass number, this is proton number or atomic number. So it will release a helium ion, mean the nucleus of the helium, of course, because it doesn't have any electrons in the outer or first orbit, so it is positive ion. It is nucleus, it is not neutral helium atom. I have already shown you the difference. So it means this element will become something else from X to Y. Of course, you know that because now, because of the emission of this helium nuclei or alpha particle, let me call it alpha particle, because helium could be confusing. So because of this alpha particle, now two protons are out of the nucleus. So as a result, this atomic number will be reduced by 2. Of course, two protons are out. And similarly, the mass number will be reduced by 4 because 2 proton and 2 neutrons are out of the nucleus. And the mass number will be reduced by 4 because 2 protons plus 2 neutrons equals 4. So here is a specific example, and this is the real example. This is how an alpha decay occurs. So here we have an element or A88. So let me see where is this element. So 88, this is radium with an atomic number 88. Okay. So here we have an element radium, and it has alpha decay. I can see that I should put a positive sign to show that it is alpha particle. So if it decays with an alpha particle, I know that alpha particle has 2 protons and 2 neutrons. So this 88 will be reduced by 2, it will become 86, and mass number will be reduced by 4. So I can see that 226 will become 222. And let me see what is this element, because now radium has become, so here is radium 88, and after 2 steps 86, this is radon. So a radium element will become an atom of radon. So you see, this is how this transformation occur, and we call it transmutation. You see the transmutation, that radium has become radon by emitting an alpha particle and of course some energy. So this is, we call it nuclear transmutation. Nuclear transmutation, just remember this word. And this is alpha decay. So now let's talk about beta decay. What is beta decay? In beta decay, an unstable nucleus, suppose Z with mass number A and atomic number Z, it emits a beta particle, right? So I told you that a beta particle is a fast moving energetic electron out of the nucleus. And because an electron comes out of the nucleus, so Z will get plus 1. Now here is the twist, because you can ask me that we know that in the nucleus of the atom there are only protons and neutrons. Sometimes only one proton. In case of hydrogen there is only one proton, but in for the other elements there are protons and neutrons. And electrons are outside the nucleus and they orbit the nucleus around them. So if electrons are here, so how does it happen that an electron comes out of the nucleus? Even if it is unstable, there are protons and neutrons in the nucleus. So how come it happens that electron comes out of the nucleus, out of nowhere? Because if it doesn't exist in the nucleus, how does it come out of the nucleus, no matter how stable or unstable a nucleus is? So here is the twist. In the beta decay, in neutron, it transforms into a proton by emitting an electron. So you see, because a neutron has no charge. And of course, if you add the charges of a proton and an electron, it is zero. They have equal but opposite charges. If you add their charges, it is zero. So charge is conserved, of course, because whatever charge is there, it should be conserved. It should remain the same. So in that case, a neutron becomes an electron and a proton. So proton remains in the nucleus, and that is why one proton. So that is why we have this Z plus 1. Z will increase by 1 because now one proton is added into the nucleus. You can imagine the situation like that a neutron has become a proton and an electron. Proton stays in the nucleus, of course, proton and neutron. Electron cannot stay in the nucleus, so it will just come out of the atom. So this is beta particle. Beta particle is just electron, but it is fast moving and highly energetic electron. That's why we have a special name for this electron. We call it beta particle. So if a nucleus is unstable and it decays by a beta decay, then you will increase the atomic number by 1 and it will release one electron, and this electron will come out of the nucleus because a neutron becomes a proton and electron. Proton stays in the nucleus, so you have to add plus 1 in the atomic number. But an electron, of course, it will come out of the nucleus and you will have some energy, of course, due to the mass defect. So if you want to see a specific example, here is carbon, atomic number 6, mass number 14. So when it undergoes beta decay, now its atomic number has become 7, plus it will emit an electron plus some energy. So you see here the situation is very interesting, and I want you to see that carbon becomes, here is carbon with atomic number 6, so it becomes nitrogen with atomic number 7. So before we saw that in alpha decay, an element was always decaying and it was going backward, or into the, it was, the atomic number was reducing, right? So it was going back in the periodic table, but now here it is going forward in the atomic table, right? Because atomic number is increasing. It has become now a nitrogen atom. The atom was initially carbon atom. It was unstable and somehow it went beta decay. So now it has become a nitrogen atom. Mass number will remain the same, of course. And so it has become nitrogen, and a fast moving energetic electron will come out of the nucleus plus some energy to balance the law of conservation of energy. So this is beta decay. Of course, beta decay can happen in reverse order as well if a positron comes out of the, but that is beyond the scope of your course, so just keep that in mind, but don't think too much. This is beta decay. And this is the interesting thing about beta decay, that a neutron transforms into a proton and electron. Proton remains in the nucleus, electron comes out. So this is why we always add plus 1 in the atomic number, but mass remains the same. So what is gamma decay? Gamma decay is easy because if a nucleus is unstable, so the reason for gamma ray is little bit different. So it starts always with an unstable nucleus. So if we know that there are protons and neutrons in the nucleus, except for hydrogen, there are always protons and neutrons. For hydrogen, there is only one proton in the nucleus. There is no neutron except for the isotopes of hydrogen. So if so in the nucleus, protons and neutrons, they have certain energy levels. I am talking strictly about the nucleus. Even in the nucleus, they have certain energy levels. So this is the relaxed energy level even. So there may be another energy level which is excited E2. Here they are in the nucleus, but they just want to release that energy to come at the most relaxed situation. So if they want to go back to the lowest energy level, which is the more relaxed state of the nucleus, they want to emit that energy, because now they are bit excited within the nucleus. So as a result of that, we have gamma decay. So it will become a more stable nucleus by releasing a gamma ray. This is electromagnetic radiation. So the effect of gamma decay is only the reduction of energy. There is no change in the mass number, no change in the atomic number. Of course, we know that a gamma ray has no mass, no charge. So it will only reduce energy of the nucleus so that it can become more stable or more relaxed. So if you want to see the specific example, we have here CO. It's cobalt. So if you want to have a look at the periodic table, atomic number is 27. So let me see, where is cobalt? 27, here is cobalt. You see? So if it is excited, as it is shown with a star on top of it, so it will go back to a more relaxed or lower level energy state of the nucleus by releasing a gamma ray. So its energy will be reduced. It is more stable. It is still cobalt. Always remember that in gamma decay, the element will not change. It is still cobalt. Everything is same. Mass is same. Atomic number is same, but it will be only at a lower energy state of the nucleus, mean it is more stable. That is the only result of gamma decay, and of course it will release excess energy in the form of gamma ray. So here I will end this lecture. I hope you have understood all the concepts, especially the beta decay, because it was interesting that how does an electron come out of the nucleus of an atom. And then we also studied alpha decay. So we also studied in detail the properties of alpha, beta, and gamma ray and particles. And we also saw the techniques and their effects, that what is the ionizing effect of those radiations, and of course the penetrating ability. So now you know what is radioactivity, what is the unit of radioactivity. Don't forget becquerel. And what is the definition of 1 becquerel? What are alpha, beta, and gamma decay and their properties? What does happen? And what are radioisotopes? And what is nuclear transmutation?